The fundamental requirement of any alternating current power grid is maintaining a strict nominal frequency. Depending on where you live, that's either exactly 50 or exactly 60 Hz, everywhere, all the time. Historically, that frequency has been anchored by machines like these, synchronous generators. They are the heavy iron foundation of traditional power generation. In this traditional model, electrical stability is physically mandated by the momentum of rotating turbines, moving beyond the capabilities of simple software-based load matching. When the load on the power system suddenly changes, the frequency wants to change with it, but the sheer physical mass of the rotating turbine acts as an instantaneous kinetic energy buffer, resisting that change in speed. The legendary reliability of the 20th century grid was a direct byproduct of this heavy electromechanical physics. The transition to renewable energy sources, specifically wind power, completely changes this physical equation. Utility-scale solar takes this a step further, stripping out rotating machinery entirely and replacing massive physical rotors with solid-state power electronics. Both of these are known as Inverter-Based Resources, or IBRs. Unlike a steam turbine, an IBR decouples the actual generation of electricity from the physical rotational frequency of the grid. As we replace heavy rotating mass with static solar panels and decoupled wind turbines, the system loses its kinetic buffer. The grid's inherent ability to absorb transient electrical faults shrinks. Without this mechanical inertia, engineers must develop high-speed digital responses to prevent rapid frequency collapse. This is the swing equation. Engineers use this mathematical model to understand exactly how a machine behaves during a disturbance by defining the physical forces acting on a generator's rotor. There are two primary opposing forces. The mechanical torque, Tm, is the rotational force input from the prime mover, like the steam or water pushing the turbine. Opposing it is the electrical torque, Te, which is the resistance applied by the generator outputting power to the grid. During steady operation, these two torques match exactly, but an imbalance results in an accelerating torque, Ta, which physically forces the rotor to either speed up or slow down. How violently that rotor accelerates depends on the H constant, or the inertia constant. This represents the stored kinetic energy of the machine, and it acts as the primary resistance to that acceleration. When a short circuit hits the transmission network, the electrical power, Te, drops instantly. But the mechanical power, Tm, cannot drop immediately because the machine's governor needs time to close the physical steam valves. Because the mechanical power is still pushing a rotor that suddenly has no electrical resistance, the machine accelerates. The internal load angle, known as delta, begins to swing violently away from the rest of the grid. If all other variables are equal, a machine with a high H constant, a heavy rotor, will swing much less. That physical mass makes it inherently more resistant to transient collapse. This chart shows the power angle curve, or P-delta curve. Engineers use it to calculate the exact mathematical limits of a generator's stability during one of these fault swings. The horizontal line represents the pre-fault mechanical power pushing the turbine, intersecting the green sine wave at the machine's initial stable operating angle. For the machine to survive a fault, it must satisfy the equal area criterion. The kinetic energy the rotor stores while accelerating, shown as the area below the mechanical power line, must be exactly matched by the energy it can dissipate after the fault clears, represented by the area above. If the fault stays on the system for too many milliseconds, the rotor accelerates for too long. The required deceleration area grows until it exceeds the available area under that post-fault sine wave. When that happens, the generator's internal angle pushes past 90 degrees. The machine can no longer slow down enough to find a new stable operating point. It overspeeds, begins pole slipping, and completely loses synchronism with the network. You can see on the graph how the generator's automatic voltage regulator and its governor try to help. By rapidly modulating the magnetic field and the steam valves, they slightly expand those available stable areas. The survival of the entire power grid in the first 3 to 5 seconds of a short circuit is entirely dependent on keeping every generator's load angle swing tightly confined within these mathematical boundaries. This split-screen visualization brings the problem of inverter-based resources back to the swing equation. Because solid-state inverters lack massive rotating metal, their physical inertia constant, H, is effectively zero. This drastically impacts a metric called the rate of change of frequency, or RoCoF. Without that heavy kinetic buffer to absorb the initial shock of a generation loss, the frequency on a low inertia system drops at a vastly steeper angle. By removing the H constant, we remove the grid's native shock absorbers. A fault pushes the system toward the fatal limits of the equal area criterion in a fraction of the time it used to take. One way to solve a lack of mass is to simply build more of it. Grid operators are re-injecting rotating weight back into vulnerable transmission nodes, but doing it without burning carbon. This hardware solution is called a synchronous condenser. It is essentially a massive, heavy generator rotor, completely unattached to any turbine or engine. Because there's no prime mover, its mechanical power input is zero. It spins freely, drawing just enough power from the grid to overcome friction, while injecting a massive H constant back into the local system. Beyond pure inertia, the spinning electromagnet provides critical fault current to trip relays and uses its automatic voltage regulator to dynamically support local voltage stability. Synchronous condensers serve as heavy, artificial anchors. They provide the exact electromechanical shock absorption of a coal or gas plant, purely for the sake of stability. This graph compares response times, highlighting the limitation of traditional turbine governors. They operate on a mechanical speed droop characteristic, meaning it takes physical time for valves to open and steam to increase. Battery energy storage systems, or BESS, provide a high-speed digital alternative for frequency regulation. Because they are completely solid-state, batteries can step up to inject or absorb massive amounts of real power in milliseconds. They arrest a steep rate of change of frequency long before under-frequency load-shedding relays are forced to trigger. Operating at sub-cycle speeds requires profound visibility. Operators rely on wide-area measurement systems and advanced AI controllers to detect fast-moving grid transients the moment they occur. In a low-inertia system, batteries synthesize the effect of mechanical mass. They simply react faster than the physics can fail. Historically, renewable inverters have been grid-following. They look at the grid's existing frequency and match it. But if there is no heavy machinery left to set that frequency, following is no longer an option. The solution is the grid-forming inverter. Using advanced control loops, these systems establish their own internal voltage reference. They actively dictate the frequency to the grid, rather than just reacting to it. By programming the right control algorithms, engineers can make a digital microchip mathematically mimic the exact power angle swing characteristics of a 1,000-ton rotor. Maintaining the synchronization of the power grid is no longer a matter of passive thermodynamics and heavy iron. The transition to a zero-carbon energy network requires rebuilding the concept of stability from the ground up. We are engineering synthetic inertia, replacing physical mass with high-speed digital control and active grid architecture.